Okay, ladies and gentlemen, let's go ahead and start our tour of Chapter 9 entitled Cratered Worlds. And as I kind of mentioned from before, this idea of cratered worlds, well, the word worlds I have a small issue with in the sense that when you think of the word worlds, what usually pops into your mind is basically planet. But it turns out that one of the two objects in this chapter isn't a planet, aka the one that's visible to you right now. This is a picture of the moon, a satellite to a planet. But the one thing that I will want you to notice, though, is for the kind of quote unquote near side of the moon, the side that we see every night, it has a different texture than the side that you see over here, the dark side, really called the far side of the moon, which is given to us in a picture from the Chinese Space Agency. And this has a very, very rough texture, whereas this over here, the near side is much smoother in comparison. So what this kind of gives us is a basis of comparison for age, aka back in chapter 7, we learned that one of the ways that we can kind of determine the age of a planet, relatively speaking, is by counting the number of craters. So by looking at these two pictures, what can you say about the age of the near side of the moon on the left versus the age of the far side of the moon on the right? Well, fewer impact craters on this side indicates younger surface. More impact craters here indicates older surface in comparison. We'll talk about that discrepancy a little bit later on in this presentation. But the first part of this chapter, it deals with lunar geography. And admittedly, I don't like this phrase of lunar geography because the word geography has a prefix and a suffix. The prefix geo means earth, kind of like when we talked about geocentric model of the universe from the ancient Greeks back in chapter 2. And the suffix graphy kind of means the study of the surface. So geography is the study of the Earth's surface. So then lunar geography is the study of the Earth's surface of the moon? It doesn't really make a lot of sense. So we're going to go ahead and say instead is we're going to call it lunography, which isn't really a word that books use, but in my humble opinion makes more sense than the alternative from before. And when it comes to kind of lunography, what we're going to say is that the lunar surface, kind of like we saw in both pictures in the previous slide, there are lots of craters from impacts from foreign objects. And what you can see right here are kind of two zoomed in pictures of different parts of the moon's kind of near side. And what I want you to notice is that many of the craters have names associated with them. For example, this crater right here is a very famous one named after Tycho, and I'll give you a guess as to which Tycho we're kind of referring to back from chapter 3. In a similar sense, there's other kind of crater names that are a little bit less well known. So for example, this idea of kind of Garcus and this idea of Ball. Over here on the right, we have Smith and kind of Resnick. Jarvis is kind of one that's also important, and Oniska, kind of more recent discovery, but that's a subjective phrase. But most of the craters that are on the near side of the moon have names associated with them because we've studied them for so long. But nonetheless, there are just a lot of them to begin with. But this idea of kind of cratering on the moon's surface, there is something that is unique about this. And we did talk about this back in chapter 8 when we talked about the Earth, this idea of surface impacts. So for example, here in this top part of the image, we have an object from space slamming into the surface, causing a depression. But all of that kinetic energy that we talked about before is transferred into that surface, creating this great pit and depression. And that kind of depression, called a compression wave in this case, it creates a pulverization. It kind of crushes and pulverizes the rock instantaneously. And because the Earth's rock, or in this case, the moon's surface, is a little bit elastic, and that might seem kind of strange, but all solid objects have a certain degree of bounce, of elasticity, some admittedly better than others. That as a result of this kind of compression wave right here from the impact, there's a little bit of a bounce, a little bit of a rebound or a rarefaction wave that kind of pushes the pulverized rock out, creating this ejecta, this kind of spray of debris that you can kind of see right here expanding outwards and eventually settling down into an ejecta blanket in this case. Now on the moon, the ejecta blanket is a little bit unique in the sense that it kind of forms streaks called rays, R-A-Y-Is, so R-A-Y-S's in this case. But the key idea is that we have an impact crater and we have this kind of pulverized rock of debris that's near the center. So this picture that you see, this is a picture of the Barringer crater, sometimes called meteor crater in Arizona. And you can see the actual kind of crater that has been produced, and the actual consistency of rock in the center kind of corresponds to the actual kind of debris that you see right here in this fracture system. Now, the picture on the right isn't actually an impact from space. This is actually military ordnance, kind of bombs being detonated. But the reason that I show it to you is that you're able to see the actual kind of pattern more or less as the kind of ejecta is kind of being released from this explosion and eventually kind of settling back down onto the surface. Some admittedly kind of far away, this ejecta blanket, some kind of much more closer, kind of like you see right here inside the crater itself. But I think the coolest part of the moon, just personally on my own level, is this idea of not Maria, but it's called Maria. And it turns out that this word has a very interesting historical connotation back in chapter 2, when we talked about Galileo. Now, when Galileo first looked at the moon with his telescope, he saw these kind of dark splotches that were on its surface. And if you go back to that picture that I showed you from his book, from his dialogal back in chapter 2, it shows kind of 4 hand-drawn pictures that he made of the moon, and part of it had a very, very dark color. It turns out that when he first saw these dark patches, he thought that they corresponded to a very specific material on the moon. What was that material? Well, Maria. To understand what that Latin word means, let's go to a similar Romantic language, Spanish, for example. The word el mar in Spanish kind of means ocean or lake, body of water, if you want to be loose about the definition. The phrase Maria just kind of means a collection of bodies of water, kind of like seas or oceans, plural. So this idea of Maria, they correspond to smooth, dark plains resulting from an ancient lava flow. But when Galileo first saw them, he thought that there was black water, aka Maria, mare, on the surface of the moon, and therefore he kind of gave it that label inappropriately. And we still use that Mare or Maria label here in 2010. And there are many different Mare, and there's even one giant one called an Oceanus that's clearly visible here on the near side of the moon. But of all the different Mare that you see, there's one that's kind of special in terms of history. This one that you see right here, this idea of the Mare Tranquillitatis. The reason that this is special is that this is the location where Neil Armstrong and Buzz Aldrin first landed on the moon in 1969, sticks out in my head. But the key idea is that this is the first place where human beings set foot on a foreign object, a different object beyond the Earth in this case. And it turns out that many other manned missions to the moon that our book talks about landed in other mare, kind of adjacent or nearby mare, because it turns out that the area there is relatively smooth, easier to land on, whereas the surrounding patches here in gray tend to have impact craters and they tend to have rougher surfaces in comparison, so they're less friendly to land on. They're more dangerous, and NASA is kind of well known for minimizing danger, so the mare is a better choice in most cases. I do believe that 1 or 2 of the Apollo missions landed not in Mare, but in something else. But for the most part, they did, just for safety reasons. Now, in terms of the actual lunar structure, we know that from chapter 8, again, when talking about the Earth, we have this idea of density that we can use to describe, in general, the composition of an object's interior. And it turns out that, just like you see right here, the moon has a very, very low average density compared to the Earth. So the value that we're going to use for this class is that the moon's density as a whole, on average, is about 3.3 grams per cubic centimeter. And as I mentioned before in previous chapters, one number by itself doesn't mean much of anything. But if you have 2 numbers, you can compare them to each other and say that one is bigger and one is smaller in comparison. The number that I want you to kind of refer back to is the density of quote-unquote rock. Technically, it's called igneous rock. I call it basaltic rock back in chapter 8, but it corresponds to just quote-unquote rock, our kind of default comparison. And if you go back to those slides, or if you go back to that part in the lecture, it turns out that the density of basaltic rock, igneous rock, was 3.3 grams per cubic centimeter. So what does this tell us? Well, the density of a chunk of rock and the density of the entire moon are the same. So this indicates that there's really not a lot of heavy material on the moon, especially when you compare that to the Earth. The Earth had a density of basically 5.5, and there's more digits beyond that, but for us 5.5 is good enough. So the Earth has a lot of metal in its interior. The moon, having a lower density, has less of those heavy materials, less of those high density materials, so therefore less metal in its interior. Specifically, it turns out that the moon has a lot less iron in its core. And you can see that represented by this series of pictures here on the top that give us kind of a color-coded comparison of the interior of different planets. We're going to talk about Venus in chapter 10. We're going to talk about Mars in chapter 10. We're going to get to those too. But focusing on the Earth, we have a green colored mantle, a purple colored outer core, and kind of a red orange color inner core. If you look at the moon, it kind of lacks a similar comparison. It has a mantle, that's true, kind of the green color, and it has a outer core, so to speak, but it doesn't really have a noticeable inner core in this case. And you can kind of see that here in this bottom picture as well. We can see that the moon has a crust. We can see that the moon has a mantle, again, kind of shown in this green color. And the moon does have a core, but admittedly, its core doesn't really kind of have a distinction of inner and outer. It turns out that the moon's core is just kind of a single entity, so to speak. Now, this picture here kind of designates temperature regions, kind of cold, warm, and hot. But the entire kind of structure itself right here in kind of a bluish color is the actual kind of core itself. And what I want you to kind of notice about this one here, the bottom picture, is that the core is relatively small compared to the size of the moon itself, aka its mantle is very, very thin, and therefore because of that, it's not going to have a lot of volcanic activity. It doesn't have a lot of the raw material for volcanic activity that the Earth had back in chapter 8 as a comparison. The other weird thing about this picture is if you look at the location of the core in this picture, something seems a little bit off, or maybe I should say off center. You'll notice that the core is actually shifted off to the right by a noticeable amount, and it's shifted in the direction of the Earth. We'll talk about what could happen, or how that could have happened in the moon's formation several slides in the future, but that is something to kind of notice, that the moon's core is noticeably off center. But the other thing that I want you to kind of notice here, though, is that this designation of hot, warm, and cold, well, because the mantle is cold, it doesn't really have a lot of lava for lava flows, and that's kind of soft evidence for no recent lava eruptions on the moon. In fact, the most recent ones were those kind of mare that we saw on the previous part of the slide, also kind of shown right here, as well as these kind of darker, blacker, grayer colors. But because the actual kind of core is only warm and hot, it turns out that the liquid part of the core is minimal, practically non-existent. And what that basically means is that the moon doesn't really have a quote-unquote planet-wide magnetic field the way that the Earth does. The magnetic field on the moon is so pathetic that if you try to use a good old-fashioned compass to navigate, it actually wouldn't be able to work. The compass needle would spin in random directions. It wouldn't latch onto a specific north or south pole the way that it does on Earth. So in terms of navigation, compasses don't work. You have to use good old-fashioned kind of GPS and star charts, like we talked about from before a little bit. But the other kind of weird thing about the moon too is that the moon doesn't have an atmosphere. The primary reason why is that an atmosphere wants to kind of bloat or escape due to its temperature. And if you don't have a strong enough gravity to hold it back down, it'll kind of bleed off or kind of escape, or as we said from before, kind of convect, if you will, away from the surface. And it turns out because the moon doesn't really have an atmosphere, it has an exosphere if you want to be picky about it, but it doesn't really have a quote unquote atmosphere. There's some very, very unusual consequences to that. So for example, here on the Earth, where we have a nice thick atmosphere, when the sun comes up, what color does the sky turn? Well, without clouds there, it turns a nice blue color. What about when the sun rises or the sun sets? What color does the sky turn? Well, it kind of turns shades of red, orange, maybe some yellow, depending upon the pollution in the atmosphere, but essentially kind of reds and oranges. But that's because our atmosphere is filled with oxygen, nitrogen, and other gases that we talked about in chapter 8. It turns out that on the moon, you see something a little bit different. So kind of like you see in these pictures here, you can see that clearly this is a picture from the moon's surface pointing towards the Earth. And you'll notice that we can see light reflecting off the moon's surface. So this is clearly daytime on the moon. But the key thing is that you'll notice that there's no kind of blue sky during the daytime on the moon. Reason why is that there's no light that can pass through an atmosphere that would trap blue light, giving us a blue sky. Likewise, there's going to be no sunrises and sunset beautiful colors like we have here on Earth because there's no atmosphere to make the reds and the oranges like we have, for example, on Earth every day that the sun rises and every day that the sun sets as well. You can see that here along with different pictures. And this one's kind of my favorite because you can kind of clearly see a bright light source, probably the sun here in the background. And you can see the sunlight reflecting off the actual surface of the moon, creating light and shadows in a very cool way. But the other thing that I want you to kind of notice is that there is no blue color to the sky, but in a similar sense, there are no stars visible in the sky at this time. We can't see stars during the daytime for the most part because the blue light coming from the sun overwhelms the faint light from the stars. We don't really see the stars until the sun goes down. It turns out there's a similar phenomenon going on with the moon. There's so much light reflecting off of the rocks getting into the camera that all that light from the foreground makes all the light in the background, the stars, pretty much impossible to see. So therefore, there really are no stars visible during the daytime in the moon, even though there is no atmosphere to make the sky blue to kind of hide them the way that it does for the Earth in comparison. So in terms of the actual kind of moon structure, there's some basic information that you have in the book. We have some basic information in the previous slides. And now what we're going to go ahead and do is start talking about the origin of the moon. And the way that we're going to structure that conversation is by focusing on different theories that attempted to explain the moon's origin, why they were kind of incorrect retroactively, because what we're going to find out is that some of these theories will apply to other moons and other objects in the solar system, so we might as well talk about them now when we're kind of introducing the moon's origin in chapter 9. So the first theory that we're going to talk about is this idea of the capture theory. And kind of like the name implies, what it basically is stating is that the moon basically was a small planet that was initially orbiting the sun, and it formed independent of the Earth. And we're kind of using this phrase of molecular cloud and accretion, which we really won't kind of be introduced to until a future chapter. But think of the molecular cloud as kind of like the womb that is kind of giving birth to all the objects in our solar system. And accretion is the actual kind of building process that creates objects like the Earth, the moon, and the sun, and so on and so on. And basically what this means is that the Earth and the moon formed independent of each other. And it turns out that, just like you see in the picture, the orbit of the moon around the sun got a little bit too close to the Earth, and Earth's gravity kind of captured the moon and locked it into a permanent orbit, so to speak, because we know from chapter 4 that's not quite true. But it kind of locked it into permanent orbit in this case. Now, the problem with this theory is that in chapter 7, we said that we were able to bring back rocks from the moon and analyze them in terms of finding the age of those rocks, the idea of radioactive dating, we said. It turns out that in terms of composition, the rocks on the moon and the rocks on Earth, they are surprisingly similar to each other, too similar for this theory to explain their independent formation, this kind of bullet point that we have right here. And because of that rock-based information, that kind of really discredits this theory of independent formation, because if they formed independently, their composition should be noticeably different, if not dramatically different. So unfortunately, this theory, even though it's an easy one, is actually flawed based upon geological or rock-based evidence brought back from the moon in the 60s and the 70s. So interesting theory, and what we'll find out is that in chapter 12, many of Jupiter's moons were kind of formed or origined in this way, but our moon, not so much. The second origin theory that we're going to talk about for the moon is something called fission theory. And the nice thing about fission theory is that it tries to explain other phenomenon, other characteristics about the moon, but unfortunately gets them wrong, as we'll find out as well. And like you see in this picture here, you'll notice that we have a giant blob of material, and that blob undergoes elongation, and there's a little bit of a kind of a bulb that kind of protrudes off the right-hand side, and it kind of eventually detaches from the central object and then coalesces, or as we'll call it, kind of accretes into a single object, forming here in figure 7, the Earth and the moon. So the nice thing about this kind of theory is that one consequence of this is that the Earth initially rotated much faster than it does today. And we know that to be true back from chapter 4, this idea of kind of tidal braking back at that time. And due to the Earth's very fast rotation, kind of figures 1 and figure 2, eventually there was a bulge or a protrusion that manifested here in figure 3 that eventually kind of ripped away, kind of like you see in figure 5, to eventually become the moon in figure 6 and 7 especially. Due to conservation of angular momentum that we talked about in chapter 3, after that kind of bulge rips away from the Earth in figures 5, 6, and 7, the Earth is going to slow down in its rotation, kind of like we talked about in chapter 4 and chapter 8 as well. And therefore, that kind of slower rotation is kind of a nice reconciling of a chapter 4 phenomenon, something that the previous theory could not do. But again, the problem with this theory is that because the moon formed from the Earth, it implies that moon rocks and Earth rocks should be almost identical, practically identical, because the moon directly formed from the Earth. And the problem with that is rocks from the Earth and rocks from the moon are similar, but they're not identical. So again, based upon geological evidence, kind of rock-based evidence, this theory doesn't really hold up. It's nice. It explains other things, but it doesn't explain the rock evidence. And because of that, we have to discard that theory, kind of chapter 1 style with the scientific method, and then move on with the process of finding the truth of the moon's origin. This next theory, this idea of the twin formation, the best way that I can explain it is basically in terms of human biology. So for example, whenever you have fertilization of sperm and egg, you have a human that is produced, basically. And the way that it kind of works, for example, with twins, is that it's possible to have 2 sperm fertilize 1 egg, this idea of twins, in effect. So that's kind of what's happening in this theory, is that the moon and the Earth are twins. They're kind of forming in the same womb, the same common cloud of gas and dust from the initial molecular cloud that everything is being born from. In this picture right here, it's called the binary accretion theory. Binary because there's 2 objects, accretion because we have gravity coalescing into a single object. The nice thing about this theory is that because the moon forms further away from the Earth, its chemical composition is going to be similar but not identical to the Earth. So the rock-based evidence is kind of vindicated in that sense. The only problem with this theory, though, is it doesn't kind of reconcile the fact that the Earth rotated faster in the past and is rotating slower now. So it kind of doesn't have that reconciliation with itself. And therefore, because of that, along with some other evidence that's beyond the scope of this class, this binary accretion theory, or this kind of twin formation theory, has been discredited, and therefore doesn't really apply to the Earth-Moon formation in this case. Now, the current theory, the one that's kind of accepted by the scientific community, is called the collision theory, or it used to be called the accretion theory. And it basically kind of goes as follows. A very, very young Earth, long ago in the past, collided with a Mars-sized planetesimal. Now, let me kind of clarify. It's not saying that Earth and Mars collided, because Mars still exists and Earth still exists. It's just saying that a planetesimal, kind of a large rocky object, kind of shown by artist depiction as this thing right here, collided with the Earth a long time ago in the past. And this collision, one nice thing about it is that when a violent collision like this occurs, it tends to change the axial tilt, or it tends to kind of rotate a planet. And because we know that the Earth has an axial tilt to 23 degrees, this is a beautiful reconciliation with that fact back from chapter 2. Now, the second picture that you see kind of shows the debris, the kind of ejecta that is kind of launched off of the actual surface of the Earth, and eventually will kind of coalesce or accrete into a solid object that we call the moon in this case. Now, that accretion process takes a long amount of time by human terms. But the nice thing about this accretion is that this accretion, it's based upon debris that is ejected from the Earth, but it's also based upon some of the debris from the foreign object that hit the Earth as well. So what this means is that as the moon is forming, it's forming from rocks from the Earth's crust and rocks from the planetesimal itself, giving the moon a similar composition to the Earth, but not an identical composition to the Earth. Likewise, as this kind of coalition, or as this kind of aggregation or accretion process is occurring, there's heat that's going to be produced, eventually allowing the moon to become differentiated, like we talked about in chapter 7. And the nice thing about that differentiation process is that, again, the heavy materials, the metals, will quote unquote sink to the middle, to the bottom of the moon. But because the Earth is going to exert a very strong force of gravity onto the moon during this kind of differentiation process, this allows the moon's core to be pulled off center ever so slightly before the mantle cools down, kind of locking the core in its kind of off-centered place, like we saw in that image. Now, based upon rock evidence, based upon the axial tilt, and based upon other factors as well, this theory gets everything essentially correct in explaining the moon's current and past behaviors. And because of that, we accept it as being kind of truthful in terms of the origin story of the moon. Something else that's kind of interesting is that the proponent of this theory, according to his story, he was able to have kind of time using a supercomputer back in the 1980s. And it turns out that supercomputers were kind of cutting edge in the 1980s. And he had to go into a military base to kind of use it. And according to his story, this military supercomputer was really designed for artillery to figure out how to kind of attack enemies. And he changed the software, which admittedly was very difficult to do back at that time. Specifically, what he did is he changed the mass of the projectile, not for an artillery shell, but for an object this size. And he changed the mass of the target, not to something like a tank, but to something the size of the Earth. And according to his story, because of the changes that he made to the hardware, and changes that he made to the software of that kind of supercomputer, the military personnel at the base were so kind of curious as to what the computer would predict would happen by that collision, that by the end of the day, because it took a very long time for the computer to run the calculations, that little kind of hole in the closet room that the computer terminal was located in, the kind of monitor and the actual kind of keyboard, it was filled with people kind of leaning over his shoulder, eagerly anticipating what the collision of these two huge objects would be. And based upon the supercomputer's prediction, it matched the kind of form and the shape and the behavior of the moon, and therefore we have our current theory in modern day times. A cute kind of story, truthful, maybe, maybe not, maybe a little bit over-exaggerated, but still kind of using modern day technology, supercomputers, to verify an astronomy theory when we really weren't there to see it in the first place. So in terms of the moon, since we've talked about it before so many times, we're going to go ahead and kind of cut off the moon at that point, this idea of its origin story. And what we're going to go ahead and do now is switch focus to Mercury. And this picture that you see right here, it's actually a very old picture of Mercury, but the reason using it is it's because it uses a technique that's very popular still in astronomy, this idea of layering. What do I mean by that? Well, this is a very old picture of Mercury's surface, and we can see lots of impact craters on its surface. So again, just like we saw in the first part of this chapter with the moon, if there's a lot of impact craters close to each other, it's a very old surface, relatively speaking. But you'll notice that there's a part of Mercury here that has a very kind of hazy appearance, and this isn't kind of like a storm or a cloud system. What this basically means is that the satellite that took this picture wasn't able to take a picture of this part of Mercury, so it should have actually been colored black due to lack of a picture. But what astronomers did is they took other pictures, specifically telescopic observations of Mercury that had low resolution, aka they're fuzzy, and they kind of stitched them into the other kind of otherwise full picture of Mercury, creating a hybrid image of satellite image versus kind of man-made telescope image, half and half. Well, a little too generous there, but a combination of satellite pictures that have good detail and telescope pictures from Earth that have very little detail in comparison. And you'll see these pictures primarily in the older telescope images, but you do see them in the newer telescope images from time to time. But in terms of Mercury, some kind of general facts. It turns out that of the 4 terrestrial planets, Mercury is by far the smallest of them. In terms of comparison, it's roughly about 1/3 the mass of the Earth. Sorry, it's about 1/3 the size of the Earth in terms of radius, and it's only about 5% the Earth's mass. So it turns out, kind of based upon that small size and small mass, if you were to stand on Mercury's surface, the gravity, the weight of your body would be very, very minimal. Not quite zero, of course, but it would be much, much less compared to the Earth, just because you're admittedly being pulled by the planet, and that planet has very little mass to pull you in the first place. Now, the reason that the moon and Mercury are in the same chapter, this idea of cratered worlds, is that they do have several things in common with each other. Specifically, they have commonalities in terms of temperature, atmosphere, surface features, and this idea of how they rotate and how they kind of revolve around a central object. And again, kind of looking at the pictures here of the moon and Mercury, kind of like we saw in the previous slides, the composition of the moon, mantle, and core, primarily solid core, but some liquid component. Here you have Mercury, you have a very thin mantle and a very large molten core, and that kind of weird dichotomy is something we'll talk about later, but it's basically a simple structure, 2 layers, orange and green. The moon was also a simple structure, purple and green, and that was it. So in terms of Mercury's temperature, well, the way that we can kind of understand this is if you think about, for example, an oven. Where is the hottest part of the oven? Well, inside the oven itself. The closer you are to an oven, the hotter it's going to be. Well, in this case, the oven is the sun, and the close that I'm referring to is Mercury. Mercury is the closest planet to the sun, so it's closest to our heat source, so therefore it makes sense that Mercury should be a very, very, very hot object. To give us some idea of how hot, it turns out that on the kind of equator of Mercury during the daytime, summer, it turns out that Mercury's temperature can get up to about 840 degrees Fahrenheit or 448 degrees Celsius. So again, how hot was it today here on Earth, even though it's been kind of raining for the past several days? It was probably in the 60, 70 degrees Fahrenheit on a real hot day in summer here in Southern California, maybe 105 degrees, 100 degrees Fahrenheit. We're 8 times that temperature on Mercury. It's insanely hot. How hot is it? Well, if you took a small piece of good old-fashioned lead and just put it on the surface of Mercury, it wouldn't quite melt, but it would become very, very soft, very kind of Play-Doh-like in terms of texture. On the flip side, though, on the nighttime side of Mercury, when the sun isn't shining on that part of the surface, the temperature can reach values of negative 275 degrees Fahrenheit, or, and there's a negative sign missing here, my apologies on that, negative 170.5 degrees Celsius. This is insanely cold because, again, 0 degrees Celsius corresponded to freezing, and we are 275 degrees below, we're 170.5 degrees below that point. So what does this mean? Well, that means that there's an extreme variation between nighttime temperatures and daytime temperatures. There's a variation of over 1,000 degrees Fahrenheit between daytime and nighttime temperature. If you think about the Earth in comparison, the temperature tonight is probably going to be 45, 50 degrees Fahrenheit. The temperature during the daytime tomorrow is going to be 74 degrees Fahrenheit. So that's a 25 degrees Fahrenheit variation. Here we have over 1,000, almost 1,100 degree variation. This is insane. Humans can't survive this variation, even with protective equipment. Our bodies just aren't designed to do it. So that's why whenever I see science fiction movies about the colonization of Mercury, I just kind of laugh and chuckle, because as an astronomer, I look at these temperatures and I just go, unless the chemistry of the universe changes, I just don't see it happening anytime soon. The temperatures are too hot to maintain habitable buildings during the daytime, and the temperatures make metals brittle and crackable on the nighttime side, this idea of negative 275 degrees Fahrenheit in this case. The primary reason for the variation in temperatures is actually twofold. The hot part of the temperature variation, it's close to the sun, so it makes a lot of sense. The cold side might not make as much sense at first, but when you think about it, it does make sense retroactively. It turns out that Mercury, like the moon, doesn't really have a thick atmosphere. And because it doesn't have a thick atmosphere, then it can't it can't hold in the heat that it gains from the sun during the nighttime. So that means that Mercury's surface and Mercury's atmosphere, but that's being very generous, get very, very cold very, very quickly when the sun goes down. On the Earth, that's different because we have a very thick atmosphere that insulates heat on a daily basis, and therefore it traps some of that heat at night, and therefore keeps the night side of our planet warm to some extent. But weirdly enough, as we'll find out in chapter 10, it turns out that Mercury isn't the actual hottest planet in our solar system. It's close. It's number 2 in terms of terrestrial planets, and also Jovians as well. But it actually isn't the hottest. The reason why is actually quite surprising, but we'll talk about that later on in chapter 10 when we get there. But one of the more interesting discoveries that was recent about Mercury is that it's very, very hot on the daytime side. But if you look at the North and the South Pole, kind of like you see in this false color image, all the color of yellow that you see right here, it isn't urine, it isn't sulfur, it isn't kind of weird stuff like that. It's a false color image where yellow corresponds to ice, primarily water ice, and the color of black kind of corresponds to shadow. So basically it was discovered that there is ice on Mercury. And we've actually seen that repeatedly. So that means that the ice actually kind of stays in an icy form indefinitely in these very specific locations. How specific am I talking? Well, inside craters. And this is important because in order for ice to melt, it needs exposure to heat. Mercury has no atmosphere, so therefore it doesn't really get hot near the surface. And especially if you're in a crater, you're in shadow. So you're not getting direct sunlight. So that means that really you're not going to be getting a lot of heat, and therefore it's not going to be getting hot enough to melt the ice at the North and the South Pole. So this kind of weird ice discovery was very, very kind of interesting for us, because at least here on Earth, in ice, there's bacteria that can survive. And if there's bacteria on ice on Earth, then maybe, and this is a supposition, not even a hypothesis, but maybe there could be bacterial life on Mercury as well. The hard part is landing on the surface, traveling to these locations, and actually kind of measuring the ice, finding these organisms, if in fact they exist. I don't see that happening anytime soon, but it's an interesting thought to kind of talk about in this case. Now, I kind of said before that Mercury doesn't have a thick atmosphere. It does have an atmosphere, but it's laughable. So basically, what do I mean by that? Well, it has a very, very thin atmosphere. Back in chapter 8, when we talked about the Earth's atmosphere and the different layers, the outermost layer of the Earth's atmosphere, we call that the exosphere. Our textbook, they kind of call it the ionosphere. I think that's a less accurate title, but this idea of the exosphere, the outermost layer of an atmosphere, is very unique because for Mercury, we've detected that there's hydrogen and helium gas molecules, oxygen, sodium, and potassium clouds, and that's being excessively generous. And there's also some kind of minor outgassing, or gases that are associated with very small-scale volcanic events on Mercury's surface. Now, the origin of this atmosphere, well, the hydrogen and the helium comes from the solar wind, aka the sun. As we'll find out in chapter 14, 15, and 16, the sun is primarily hydrogen and helium, and because Mercury is the closest to the sun, it's really not surprising that this would kind of permeate Mercury's atmosphere to some extent. The oxygen, sodium, and potassium clouds, their source is interesting. Kind of like the Earth's atmosphere back in chapter 8 came from comets. They're ices and kind of materials vaporizing, turning into gases. The same thing happens for Mercury as well. It doesn't get hit by meteors very often or comets very often anymore, but when it does happen, that material can vaporize and form a very, very thin layer of the exosphere. And this idea of kind of outgassing from volcanic eruptions, you have things like sulfur dioxide, carbon dioxide, and a few other gases as well. But it turns out that, again, it's very, very minor in this case. So what are we kind of talking about here? Well, in terms of percentages, and this is relatively old data, 2003, but based upon that old data, most of the exosphere of Mercury is oxygen, this kind of red color right here, O2. You have a very large amount of sodium, about 29%, about 17 years ago. And then you have this idea of hydrogen, 22%, helium, 6%, and then kind of potassium, along with everything else kind of being about 0.5%. It turns out that the atmosphere of Mercury is dynamic. It changes because its atmosphere is so thin to begin with. So what do I mean by that? Well, Mercury is very, very hot. So the heat that it absorbs during the daytime makes the actual kind of gas want to kind of convect or kind of rise further away from Mercury's surface. And again, because Mercury has a very thin atmosphere, it's very easy for those gases to bake off of the surface and never come back down to be maintained. So gravity pulls downward. Kinetic energy, aka the temperature of the atmosphere, wants it to bloat away from the surface. And it turns out that some of these molecules over time escape because kinetic energy is greater than gravity, so therefore we have escape velocity that is reached, and they escape from the weak gravity of Mercury, changing its composition in a noticeable kind of way. Now, in terms of Mercury's interior structure, we were able to figure out the interior structure of the moon by landing man-made spacecraft on the surface and measuring moonquakes, kind of like how we did for the Earth back in chapter 8 with determining its interior structure. Now with Mercury, we can't do that because the temperature of the parts of the surface that we would land upon are too hot, and therefore our equipment wouldn't work very, very quickly. But based upon man-made satellite observation, radar and things of that nature, what we've been able to kind of determine is that, kind of like you see in this picture, we know that Mercury has a thin crust. It has a mantle that's very, very thin. It has this kind of weird layer of solid iron sulfide, and that's really not mentioned in other pictures, so it's really not super important for us. but we think that it has a liquid middle core. This is kind of like an outer core basically, but it has a liquid part of its core and then a solid inner core as well, similar to the Earth and how it's kind of labeled here. But this is a little bit disproportionate. This is not to scale. If you look at the picture here on the right, this is to scale. So you notice that the Earth has a very large core, a very large mantle, and a very, very thin crust on the top. If you look at Mercury, based upon its appearance, its volcanoes, and other kind of geology, if you will, on its surface, we kind of estimate that its core is insanely large, its mantle is pathetically thin, and its crust is a little bit thicker than the Earth's in comparison. There are reasons for that, and our book does mention it, but it's really kind of heavy on the geology, so I'm going to go ahead and dance around that in a very kind of odd type of way. But it turns out that the kind of evidence that we have geologically, rock-based, for this bizarre structure of Mercury have a very interesting kind of origin story behind them. It turns out that kind of like the origin story for the moon was based upon a collision, we believe that the reason that the mantle of Mercury is so thin and its core is so large in comparison is kind of like you see in these two pictures. We think that long ago in Mercury's past, there was a large planetesimal, a large object, kind of shown here on the right, that collided with a very, very, very young Mercury. And that collision, because the objects were so close together in size, unlike the Earth where there was a noticeable discrepancy, because these two objects are pretty close together in size, it doesn't blow the planet apart, kind of Star Wars style, but what it does is it blows off the outer layers of Mercury. Its original crust and most of its mantle are kind of blown outwards as ejecta, kind of shown right here as these kind of rock fragments, for example. Some of those rocks will eventually settle back down, kind of like you see right here in these kind of little artist depictions of kind of bright white light. So it will eventually form a new surface, and therefore it's going to have what's left of a mantle, which is very thin, and it's going to have a very kind of bizarre crust on top, kind of like we see in modern day times. But this kind of weird collision theory is supported by the fact that there's other evidence on Mercury which kind of lend itself to this as well. But before I get to that evidence, let's go ahead and kind of look at Mercury's behavior as it goes around the sun, this idea of rotation versus revolution, kind of like we did back in chapter 8 for the Earth and 4 to a lesser extent. If we look at this first picture here of Mercury, this is going to be our reference point, our starting point. Day 0, noon. And what do we mean by noon? Well, imagine that this arrow here is you looking straight up in the sky, kind of like at your zenith. And what you'll notice is that the sun is directly above you at your zenith. So it's new time in this case. It turns out that Mercury goes around the sun counterclockwise, and it rotates also counterclockwise by this white arrow right here. So what happens is that basically in this picture, at day 0, you're kind of facing west in like a compass direction. 15 days later, as you're looking up in the sky at your zenith, the sun has kind of started to set in this case. And therefore, when you look up, you see not the sun, you have to kind of look to your right, closer to your horizon to see the sun. So the sun is kind of setting 15 days later. The sun is still setting 30 days later. We're kind of facing now east, not west. After about another 14 days, you're now facing kind of north, but it turns out that this corresponds to sunset basically. So you're looking straight up, the sun is not directly ahead, it's kind of barely visible up kind of around your horizon, your true horizon in this case. Starting with day 45, going to kind of day 59, you're now in darkness because you're looking straight up in the sky and you're now facing away from the sun. So therefore it's dark in this case. So basically what it means is that on Mercury for about 45 days, for right now at least, you're basically in sunshine going from noon to sunset. But the key thing here is that if you look at this orientation here in the kind of peach colored, you'll notice that the arrow is pointing left. So your zenith is over here. So after 59 days, you are looking west. So what this means is that one sidereal day where the stars that are over here go back to the zenith has occurred after 59 days. But after 59 days, you're still not looking at the sun. So one solar day has not been reached. We still have to keep going. If we fast forward to day 74, it's still nighttime, but we're not quite approaching midnight. We're getting there in this case. Once we hit day 88, you're looking directly away from the sun. So therefore it's midnight at that time. So to go from noon to midnight corresponds to one complete orbit around the sun, aka kind of 1 year in this case. But you're facing the wrong direction. It's not quite noon yet, so we're not at a solar day. We're kind of quote unquote halfway there, so to speak. So it's nighttime at midnight after another almost 15 days. It's still nighttime, but it's getting closer to the dawn. Day 118, dawn is approaching. Day 132, dawn is approaching. If we go ahead and kind of go back to day 118, you're noticing that you're facing west again. So from day 59 to day 118, we now have one more sidereal day at this point. So 59 plus 59 adds up to 118, so that does kind of make sense. So 2 sidereal days, 1 plus a little bit extra orbit around the sun. Day 132, it's now dawn. Day 147, the sun is rising a little bit higher, not quite at your zenith, but getting there. Sun is kind of rising, day 162. And now when we get to day 176, now the sun is at your zenith. It's now noontime again. So the way that it works for Mercury is that Mercury rotates very, very slowly as it revolves around the Earth, such that one solar day on Mercury from noon to noon corresponds to 2 years, 2 trips around the sun. Now, in terms of sidereal days, it's lesser. And this is why we like sidereal days in astronomy, because sidereal days are smaller for a planet like Mercury, only 59 days to go from stars in the sky to the same position in the sky, to the same position in the sky, to the same position in the sky again. Now, the moon has a similar behavior in the sense that the moon had a synchronous orbit where its speed revolving around the Earth and its speed rotating were the same, and we only saw the same side. Mercury isn't quite the same. It turns out that for every 2 trips around the sun, we have 3 sidereal days. So there's a 3-to-2 ratio for Mercury, whereas on the moon, it's a 1-to-1 ratio. So 1 sidereal day on the moon, called a sidereal month, but a sidereal day in effect for the moon, corresponded to kind of 1 year, 1 trip around the Earth in comparison. So the moon had a 1-to-1 ratio, Mercury has a 2-to-3 ratio in this case. Similar in the fact that they're integer values, but not quite identical. So similarities and differences, and take that into account as you will. But it turns out, kind of going back to this idea of evidence for formation, 2 of the most noteworthy things on the moon are what we call the Caloris Basin and scarps. And what I want you to notice is that the Caloris Basin here on the left, if you kind of use your imagination, you can kind of see that I'm tracing out a circular shape. And that circular shape that I'm tracing out corresponds to an ancient impact that occurred on Mercury's surface. And that's important because on that previous slide, the hypothesis, the theory, if you will, that we're kind of using for Mercury's bizarre interior was based upon a collision in its past. So it's possible that the impact producing the Caloris Basin was violent enough to kind of produce the actual kind of impact on its surface. Now that's circumstantial. There isn't direct evidence of that. We have to bring back rocks to verify. But it is kind of a promising idea to start off with. How big is the Caloris Basin? Well, basically it's about 1,500 kilometers, basically about 800 miles in diameter. To give you some sense of size, it's roughly about the size of Texas from end to end. And it turns out that this kind of collision was so big that it had weird consequences. And I use that word kind of as a foreshadow of future slides. But the Caloris Basin was a huge impact, and its kind of impact on the other parts of Mercury will be seen in a couple of slides. But the other picture that I have here on the right are scarps. And it turns out that scarps give us actually a lot of direct evidence. Well, direct is a strong word. They give us a lot of evidence for the collision aspect of Mercury and the cooling down from that new crust formation of Mercury. The way I can explain this best is, think about a grape. Okay, well, if you take a grape and you dehydrate it, it turns into a raisin. Okay, well, if you think about the shape of a raisin, it has a very kind of wrinkly texture as a result of the dehydration process. It turns out that scarps are something roughly similar, we think, on Mercury. Scarps, or escarpments, are basically cliffs on Mercury's surface, and there are a lot of them. Surprisingly many, too many compared to the Earth. And the best that we can kind of use to explain so many and so large escarpments or scarps on the kind of Mercury surface is that as Mercury's surface was cooling down from a very violent event in its past, probably a collision, that cooling down caused its surface to kind of wrinkle up in this case. And it turns out these escarpments here, these scarps, this arrow here in particular, this scarp is casting such a large shadow that we can see that black shadow right here, and to a lesser extent the one over here as well. And it turns out that some of these scarps, kind of like the one right here, they can be as large as 1 mile in height. To give you a comparison, the largest building on Earth is the Burj Khalifa, seen right here. It's a little bit less than 1 mile, basically. It's about 800 meters, about 1,500 feet, give or take, and it's less than 1 mile high. And some of these scarps on Mercury are taller than this tallest building on the Earth. Not all of them are, but admittedly some of them are, and that's very, very dramatic. That indicates a very kind of interesting cooling down, wrinkling event on Mercury's surface, and again, giving us kind of indirect evidence of a collision in its past and a kind of very quick cooling down, crinkly behavior that's occurring. But my favorite thing about Mercury is something that's called weird terrain, and you can see 2 different pictures from 2 different satellites right here of weird terrain. And the reason why it's called weird terrain is that when it was first discovered in the 1970s, it was a feature of Mercury's surface that geologists could not explain at that time. It had no similarity to Earth's surface at all. So geologists were mystified and perplexed as to what could create this exact kind of crinkly shape to Mercury's surface. Kind of better seen right here, seen to a lesser extent in the bottom picture. But it turns out that geologists, their best theory as to what creates this kind of crinkled texture, and to give you an idea of how crinkly I'm talking, if you go into your kitchen and take a sheet of aluminum foil, it's initially smooth, go ahead and crinkle it up and then go ahead and try to flatten it out. Your crinkling of the aluminum foil has kind of permanently changed shape, making it kind of weird in texture. And geologists think that something similar happened on Mercury as well. Something crinkled its texture, causing it to kind of crack and fragment in very, very bizarre ways. And one event that could explain that is the impact of the Caloris Basin. Because it turns out, interestingly enough, this weird terrain is on the exact opposite side, antipodal, as our other book called it, as to the Caloris impact over here. And what we kind of think is that the impact was so violent, it created huge shock waves, huge earthquakes that traveled through Mercury's interior and through its actual kind of surface as well, such that they kind of coalesced together on this opposite antipodal side. And that kind of coalescing of earthquake waves, our S and our P waves from before, basically kind of crinkled the crust that was very stiff and rigid at this point, causing it to kind of create these weird crinkles, cracks, and kind of weird terrain as a consequence. So with that kind of being stated, this last fact about Mercury ends chapter 9 for us, and now we'll go ahead and transition into chapter 10 in the next video. Thank you for listening.